Okay, good morning, everybody. So, I hope you are having fun. And this morning, I have two lectures. One is on optimization methods, and then the second lecture would be on seismic inversion, where you will see the application of these optimization methods. Okay? All right. Okay, so what I'm going to talk about this morning includes like what is optimization. And I already talked about norms, but I will sort of, revisit that just so that everybody is on the same page. And least squares, which I have talked about several times, I'll very quickly remind you of that. And this term regularization, that also is something we discussed. And then I will talk about nonlinear problems where we need to use optimization methods. So far we have been talking about linear methods, right? And in linear method we saw that we could use least squares. But this norm and regularization, these two are common, okay? Whether you are doing solving a linear problem or a nonlinear problem, in either case you have to come up with a measure of the misfit or error. And also, you have to think about how to get a stable solution, and for that, you need to introduce some kind of regularization. And I will essentially talk about some of the most popular methods without everything, but in sufficient detail so that you understand how it works. Okay? So there are different methods like steepest descent, then a variant of steepest descent. There's another method called conjugate gradient, which addresses some of the limitations of steepest descent. And I don't think we can really strictly call it a variant of steepest descent. Then we have something called Newton method. And what I would really like to draw your attention to are some of the newer methods which are quite popular in machine learning training. And those are variants of steepest descent. These are called stochastic gradient descent. Then there is something called ADAM. And I will also talk about making use of mini batches of the data to improve efficiency, okay? So why do we need to talk about optimization? Well, we talked about, we have our data D, and from there, we want to know about the model M. And we also know how to generate our theoretical data. And theoretical data or synthetic data is given by some equation involving M. Okay? Well, M is a set of parameters that you're interested in. So if you use some model vector, and then solve this equation, it will give you theoretical data. So what we do here is then we want to compare it against observed data. And for linear problem, we had this D theoretical was GM, right, which is basically matrix times a vector. And we define a error function. So what we do in inverse problems is we compute our theoretical data using our forward model, and we assume that we know what the forward model is like. But in case of machine learning, we don't quite use the same G because we assume that we don't know G in general. There are some machine learning algorithms where you can use this forward modeling operator G also, but in general, we assume that we don't know the physics of the problem. So we have some training data, and then we fit it into some model. And this model is the machine learning model. Now this is different from your model parameters M that I'm talking about. And this is essentially some big function f, which is a function of d, which is your input data, and w is the other parameters. When I use machine learning, I'll use w because that basically means we have these are the parameters, we call those weights. And also I'll change the notation and I'll say that my input is x. So it's a function of both x and w. And it gives me a prediction of our target y, right? And I call it y hat because it's not going to be exact. So if you have our inverse problem, we do d, we operate on g, and that gives us the theoretical, right? For an assumed model. In some machine learning, we put x, we have a function of x and w, we get an output y. So in both cases, we have theoretical data and we have prediction. We have prediction and we also have actual observation, right? Theoretical data is the prediction. So now what we want to do is to find the difference between those, right? And we define an error function. And in the machine learning community, the error function is called a loss function. It's basically the same thing. So don't get confused if they say loss function, okay? It's also called cost function, it's called listed function, objective function. So, error function, cost function, objective function, loss function, misfit function, all kinds of names we have. So this is a function that measures the difference between your observation and the theoretically computed data. And then we use this method called optimization. There are many optimization methods. We'll talk about some of those in a few minutes. With the hope that this optimization method will give me an optimal set of model parameters, okay? And what is an optimal set of model parameters? A set that when used to solve our forward problem will predict the data as close as possible, okay? So remember our linear regression problem, we were fitting different straight lines, right? And the straight line that gives the minimum error is our best fit model. And for best fit model, I have two parameters, there is the slope and the intercept, right? The difference between what we did then and what we'll do now is that there we actually just did a one-step inversion. But here we'll do it iteratively, okay? Predicted output is the data, observed data and synthetic data, okay? That is what it predicts. And then we repeat it until your predicted data and the observed data are very similar, okay? I would not say, why you don't want the error to be zero, right? We talked about that yesterday because there could be overfitting, right? Okay, so let's look at this curve here. This is a hypothetical error function or loss function for a variable x, okay? So as you change the value of x, which can be, so let's say this is my m or w, and this is my f of m, okay, or w. So as you change the m, it actually changes, the error changes from high to low, then again high, then to low, then high, then low, and so on, okay? You'd be lucky if this error function was more like this, so that there is only one well-defined minimum. But in real world, for nonlinear problem, your loss function is multimodal. It has multiple peaks and troughs, okay? So there are some names. These are all points of minimum, right? And these are called local minimum. So then there are two types of local minimum. Could be a strong local minimum or it could be a weak local minimum. And the minimum of all minima is the is the global minimum. The global minimum can also be strong or local. But global minimum is a part of the local minimum, but this is the minimum of all minima. Okay? So what is a strong local minimum and what is a weak local minimum? So I'll keep this slide of half of it up here. Remember I talked about putting some prior or something like that. So let's say that I have some feasible region. So if this is your some say density parameter or velocity parameter, so let's say it's a density, and you know that the density can be between say 2 and say 6 grams per cc. So then this region, which is basically between 2 and 6, will be called a feasible region. You don't want to find a minimum which is outside of the feasible region. Okay. Of course, you can ask me, how do I know what is my feasible region, right? But that is something that comes from your expertise. If you don't choose your feasible region, you'll never find the minimum that you're looking for. Okay? So you have this feasible region. So then it says that, let's say that in this feasible region, I have a point. And I consider a small neighborhood around that point. Okay? And what it's saying is that, let's say that this is my, say, M star. And if I go a little bit, just very little, either to the right or the left, if my error increases, then that will be called a strong minimum. Okay? On the other hand, if you go a little bit away and the error does not change much, that will be your weak local minimum. So if you were to ask me, like in geosciences or geophysical problems, what kind of minima are expected, I would say both kinds are possible. It all depends on your data and your physics of the forward problem. Okay? So our job is to find the minimum, right? So how do we find the minimum? You have already, yes?
I have two questions.
Please.
Yes. The first one is, what is the input for the generation of that predicted data? And the second question is, under what terms or under what conditions do we speak about the issue of global or local? What is the local, what is the global?
I already told you. First of all, your question is, how is this curve generated, right?
The input.
The input to this is a forward data. So you have some observed data, right? You observe. This is what you have observed in the field. And now you are computing a synthetic data. Okay? And for that, this is a function of some model n, right? So this d sen has been computed by your forward operator. So you've done a forward calculation. Okay? So let's say that you are working in, say you're working with resistivity data, right? So you go to the field, and then you basically measure apparent resistivity, right? As a function of x or AB by 2, whatever they call it. Now you have an equation, a set of equations that can give you this apparent resistivity curve for different values of resistivity parameters, right? So you start with some values, and that can give you this theoretical data and our synthetic data. You look at the difference between these two, and this could be simply the sum of the square or some other measure. And then for different values of this, I can compute this curve. Now I'm showing it only for one-dimensional problem, theoretical. But in general, you have a lot of parameters, and you won't be able to generate this curve because it's going to be in multidimensional space. Okay? Yes?
I mean, that is the apparent resistivity of the apparent resistivity that generated, theoretically generated. Actually, I mean, finally, we need to determine the true resistivity, right? how to improve the true resistivity by optimizing the result. How can we improve the true resistivity?
Yes. So this curve is telling you that the best resistivity would be somewhere here, because this is the minimum, right? And these are okay, but not the best. So looking at this, you can see that as the minimum error. But again, minimum error with the constraint that it will not fit in noise. Okay, so you have to be careful about how we define this loss function.
Every iteration, at some point it will reach one point.
Yeah. So, but then how do you find this point? That is what optimization is all about, and that's what I'm talking about next. Okay? Okay? Good. Any doubts, please interrupt. Yes.
So this D minus Dn, that could be, it could also be N1 or N2, either way. So it's just a function.
Yeah. Okay. So now that we have defined strong and local minimum, let's now think about how do I find the minimum, right? So let's say in calculus, I think you have been taught how to find the minimum of a function, right? Of a single variable. How do you find that? You compute the gradient and set that equal to 0, right? But then you have to also look at the curvature or second derivative, right? If you can say the gradient here is 0, and in this curve, gradient here is also 0. So this could be a minimum or a maximum, right? So you have to look at the curvature, which is given by the second derivative. So the necessary condition is that L prime W is equal to 0 and L double prime is greater than or equal to 0. Okay? Our problem is harder than that. Our problem is that we have a lot of parameters, right? So let's say that I have a model parameter vector that has 3 parameters, okay? And our loss function, and this is my M vector, our loss function is L(m). Now we have to take the derivative of this, right? So I need to calculate del L del M. How do you compute the derivative of a function of multiple variables? Take partial derivatives, right? So how many derivatives you can have? You can have one del L, del M1, you can have del L, del M2, del L, del M3, and so on, right? Depending on how many parameters you have. So your gradient, our first derivative, is now a vector, right? And you want that vector to have 0 length, right? So we look at the norm of the vector and set that equal to 0. Okay, so that gives me minimum or a maximum. But then what about the second derivative? So for second derivative, we look at what we call a Hessian. So when you take second derivative of a function of 3 variables, what do you have? You have del 2L del M1 square, you have del 2L del M1 del M2, del 2L del M1 del M3, right? Similarly, you can have del 2L del M2 square, del 2L del M2 del M3, and then you have del 2L del M3 square, and it's a symmetric matrix, so these are going to be here. So now that's your second derivative. So as soon as you go into a function of multiple variables, you can no longer deal with the scalar gradient and scalar Hessian, scalar second derivative. You have to have a gradient vector and a Hessian matrix. So how does this idea of curvature greater than or equal to 0 apply to multidimensional case? What we do here is simply look at this property of this matrix. And if this matrix is positive semi-definite or positive definite, then we know that it's a minimum. Okay? So this is assuming that you have a quadratic error function. So you can ask me, like, my error function actually has multiple minimums. So how do I know that I'm at the? Why should I assume that it's a quadratic, means one minimum, right? Yeah.
In that function.
Yeah.
No, like in the last, like when I L prime W equal to 0 and then there was lines both sides. What is that term?
Oh, that is the second derivative. The first derivative has a single prime and second. Yeah. You're talking about this and this? Here. Just a sec. Oh, you're talking about this. That is the norm. That is a sign of the norm. And we'll talk about that. We already talked about, norm of a vector. And so, yes, good question. This is actually the norm of the vector, which measures the length of the vector. Okay? Yeah.
Sir, if we take the second derivative of any function, what will come to mathematics? So, if greater than 0, second derivative greater than 0, at that point, the existing function gives the maximum value. Here, we are searching for minimum.
Yeah. Oh, so this is all I'm talking about, is optimum value, right? Yeah. See, that either it has to be positive or negative, right? Yeah. That's why I drew this curve somewhere. That in a second derivative, just getting the first derivative is not sufficient, whether it's a minimum or maximum, right? Okay. So now I will talk about, so I'm assuming that you all have had some background, you have had some courses on linear algebra where they talk about, linear system of equation and all kinds of transpose adjoint, and I don't have time to discuss those, but these are some essential concepts that you have to have, like eigenvalues and eigenvectors and so on. Okay, so here I want to revisit this because we talked about this in the very first lecture. Vector norms. How do you measure the length of a vector? Well, this is our, let's say that I have a two-dimensional vector. I have a vector in two-dimensional space, and that's my point, right? And if this point is x1, y1, how do you know the distance of this point, or length of this vector, measured from origin? What is the common procedure? So that's just to be consistent with notation. Let me call this x1 and this as x2. Okay. So I have this vector here. Okay, and let me call this as vector x. Okay, so what is the length of this vector? Generally, x. So it is basically x1 squared plus x2 squared, right? This is your standard Euclidean norm. Okay, in Euclidean geometry, this is what we use. But as I explained to you earlier, we can have, this is called a norm. Okay. And there are other ways you can define the distance. And this is your LP norm, where you take the absolute values, raise them to the power p, sum those, and then take the pth root. And when p equals 2, that's your L2 norm. And this is also called Euclidean norm, right? Or Euclidean distance. And when you take the absolute value and sum those, this is sometimes called, this is an L1 norm, and this is sometimes called Manhattan distance, okay? Okay, and the other day in the first class, we talked about the effect of the choice of the order of norm in this square fitting of straight lines, right? So you know that it does make a difference. So here is the example that I showed you earlier. I just wanted to remind you that this is basically, these are the points, and you can see what L1 and L infinity does. And you also saw that in that notebook, I showed you an example of using L1 norm, using lasso, and you saw how that affects your solutions. Okay, so this is something we already talked about. One thing that I think women will maybe talk about is when you have categorical variable, like 1, 2, and other things like that, the loss function, you cannot use the same concepts of norm for defining the loss function, because you're looking at the difference between 0, 1, 2, 3, 4, things like that. So what they do is something called, this is called the hinge loss function, and sometimes they use an entropy. And this is something probably we're not going to discuss in the class, in the lectures, but I leave it on the notes so you are aware that when you do a classification problem then you have to use some different norm than what we normally use. Okay? Okay, so least squares. This is our linear problem. We are continuing to discuss how we find the optimal model parameters, right? So in the least squares, also we define a norm, and the name implies that we use an L2 norm because it's finding the least value of the square norm, right? That's why it's called least squares. And here I didn't put the square root because that really doesn't make a big difference in terms of the final equations. So we take this L, y minus gm transpose y minus gm, and then 2 del L del m equal to 0, and that gives you this GTG inverse and GT. And we went and we discussed this at great length with an exercise, so you all are familiar with this. So for linear problem, this is just one-step procedure, okay? But this is also not as simple as you think it is because of the rank deficiency of this matrix, right? You saw that in the tomography problem, the straightforward inversion didn't work, right? So then we had to play some trick to find your gas, right? And that trick was making use of some regularization. So when we use a minimum length constraint, we get this thing called damped least squares. And I talked about this. So all that you have done here is your objective function is d minus, what did I use here in notation? Or y minus gm, because y minus gm transpose, y minus gm plus epsilon square m transpose m. Okay? And this basically assures you that your model length is minimum. Remember, this is the measure of length in L2 sense. Why do I say that? Is everybody familiar with this notation? Okay, so let's say that I have this vector x, okay? And no, let's stick to m only. So let's say m is a vector, and this is m1, m2, m3, right? And normally you write this as a column vector, right? So what is M transpose M? M transpose M is column times row, right? Because they have to transpose it. Yeah. And if you sum those properly, you get M1 square plus M2 square plus M3 square, which is your measure of the length, right? So putting this constraint as M transpose M basically assures you that your length of the model is small. And it turns out that with that constraint, we get a new formula, again analytically derived. Okay, you simply take the derivative of this loss function, del L del M, and set that equal to 0, and that gives you this. Okay? And this alpha, epsilon or alpha, this is your damping parameter, which you guys worked very hard to find out the value as well, right? It was very hard to find the value that actually works the best for you, right? Okay. Now we can also apply other constraint. I think somebody asked me, what if I have some prior knowledge of the solution? So here what I can do is I can put in, again, some epsilon square or alpha square, M minus M transpose M minus M. So this is the difference between the answer and the a priori model. And you are minimizing the difference between the two. That means you are allowing the model not to go very far from your a priori model. So this is how you can put a constraint. You could also say that I want to apply a smoothing on the model. How can you do that? You can say that I have my model, which is, say, M1 and M2, and then or M3 and things like that. I can multiply it with a matrix. And if this matrix is, say, minus 1, 1, minus 1, 1, so then all it does is simply multiplies, and that is basically smoothing it, right? And they don't even have to be minus 1. It could be 0.25, 0.5, and things like that. So it's essentially a running average. So this will give you a smoothness constraint, okay? And that smoothness matrix is D. So what you have to do then is so this is your data loss, which is simply, D minus GM transpose. And you have this dm transpose dm, right? So this is going to be your m transpose d, and m, and this matrix you can represent is as W. Okay? So this is more like a weighting matrix. Now this matrix can be, so this is actually a first derivative matrix, finite difference, that ensures that your first derivative is very, very small. But you can also use a second derivative operator or any kind of smoothing you want, but make sure that this. Now this definition of loss function is not restricted to linear problems. You can use the same definition for the nonlinear problem.
D as the identity matrix.
No, we don't use D as an identity matrix. All we do here is this D is already in G, right? This identity matrix, and this is basically epsilon square. So earlier we had only G to G, and this G to G, so D is this Y actually. Okay? So it's outside. So this is inverse operator. Okay? Yeah, I'm sorry for using different notations, but you have to be familiar with this notation also, because this course is about both inverse theory and machine learning. Okay? Okay, so in general, you can have some weight on the data, and you can have some weight on the model. Okay? And you can get a least square solution also. So in general, you can have an LP norm of model and an LP norm of data and LP norm of model. Okay? And this P can be different for different, whether it's a data norm or the model norm. Okay? All right. Now,
M within the brackets.
so that's your parallel model. Okay, something that you believe your model should be close to. Okay? This is what you are actually solving for. And this is your a priori knowledge. Like if you say that I'm solving for density, and you don't want your density to be very far from, say, 2.0, then that W will be 2.0. Which M we are talking about? This one? This one? Oh, here. Okay, so I've missed a minus sign. It's the same thing. M minus M prime. Yeah, thank you. If you know it, then you can put it in there to get a better constraint solution, but you don't have to have that. Instead, you might want to choose some kind of smoothness operator or some other constraint, because most solutions are non-unique, as you saw with the tomography problem. Okay? Okay. So what is optimization? Now we'll go into nonlinear problem. So in nonlinear case, your loss function would be D minus GM transpose D minus GM. And here I have chosen this G, which is not a matrix anymore. Okay? So here, in that case, you can have a complicated loss function and you want to find the minimum. So what is optimization? Optimization basically is a method which basically which measures, which finds the minimum of the minimum or maximum value of a function. That's all. But it's much more difficult said than done. So how do we find the minimum? Okay. And these are local optimization methods I'm talking about, because it assumes that there is one well-defined minimum. Okay? So pay attention to this algorithm. We assume that our function is differentiable, so you can compute its derivative. And we start from an initial guess. Okay? So let's say that you're trying to find velocity of a particular layer. Okay? So you start with an initial guess. Let's say that you assume that it's 2.5 kilometers per second. Okay? But the actual value can be 3. So you start with one value. And this is a multidimensional problem, right? So you can have multiple layers with different velocities. So you can have a starting model that has a whole bunch of starting values. And that's your initial model. And the first thing you do is to evaluate the loss function, right? And the loss function, you're solving a forward problem. So once you get the value of the loss function, you check whether this is actually greater than or equal to a small number, because you have to set some threshold as to how small you want your loss value to be, right? So if it's not already the minimum value, then you have to decide how I want to update my starting model, right? So for that, you need to find a direction. So you can think of this three-dimensional space. Here I have the landscape of the loss function, right? And I am here. This is my starting model. And somewhere in this room, I have that minimum value, right? How do I find it? We don't know. So you have to choose a direction in which you want to go, right? And you also have to find out how far you want to go. So you need to find a search direction, and you also have to find out step length. So search direction, step length is also called learning rate. So once you know the search direction and you know the step length, then you can update your model by adding this perturbation. Okay? Now, you might ask me, like, how do I find the search direction? That is something I'll talk about next. And then you do it repeatedly until you have found the minimum value of the loss function. Okay, so that is the basic philosophy. Okay. So, yes.
Random initial model.
If you don't have better information, then you can start at any random initial model. But that does not guarantee that you will find your solution very quickly, or even you'll get the right solution. So if you don't have good information, then you can start with different random guesses each time and run it for a few iterations and see which one is better. Okay? And that's a very good question, because this is what you will run into all the time in solving an inverse problem. Okay.
Local minimum.
Yes, so local methods will give you local minimum only, and you have to be happy with that. These are faster, that's a good use. Okay?
Don't we have any algorithm which can jump out from the local?
Yeah, we'll talk about that. The global local optimization methods. Those are more expensive, but that's what basically my specialty is. I don't mind. I don't mind global optimization. Okay. So, the first method that I'll talk about is steepest descent. In steepest descent method, what we do is we compute the gradient of the loss function. Okay? And this step length is generally computed by Charlotte or some fixed or some number. So how does this work? Let's say that this is my loss function. Okay? And that is my starting guess. So I compute the gradient of the loss function. Now the gradient gives you the direction in which the function is increasing. So you go in the negative direction of the gradient. So let's say that you come here, and then the step length basically gives you this is where you need to be, right? Then you compute gradient again and find a direction, and you repeat it, and maybe after a few iterations, you will find this minimum. So at every step, you have to be able to compute the gradient. So not only you need to evaluate your loss function, but also its gradient. Okay? And this is called gradient descent. It's a beautiful method, and you can see that it takes multiple steps to find your minimum. Okay? So a lot of optimization problems are solved using some variants of gradient descent. So there are parameters like, this learning rate, which are the step length, right? And this is a picture that tells you what is the strategy one should use. A very high learning rate will basically, rather than converging, it will diverge. And a high learning rate may actually converge to suboptimal place. If you use a very low learning rate, then the convergence is very, very slow. It might take 10,000, 20,000 iterations, and you don't want that. So you want to choose a learning rate that actually steadily decreases the loss function. And that is something like you have to do something pretty much by trial and error. So this is one hyperparameters. How many iterations you want, and what is the learning rate? These are things that you have to basically try and see. Yeah. Yeah.
Initially, we started with 1 point at the top. Then we are coming towards the wrong side.
Yes.
How we can get to know when we need to stop at that point? We can move to the next also.
Yes. So how do I need to know how to stop, right? So there are two things. each time you are calculating the error value, right? A loss function. So you can put a threshold, like how low I want to be, okay? And the other thing, and that's what works the best. And the other thing is you can also say, look at the gradient and look at whether my model update is big or not. If the model update is very, very small, then you know that it cannot go any further, okay? Very good question. Any other questions? You see, when you look at this, you think about yourself running this and say, what are the questions that can come in your mind? Okay? Yes. Yeah, okay.
Here I tried with one synthetic emulsion, sir, by using synthetic data. Initially I had taken 100 iterations.
Yeah.
So after 30 iterations, it is keep on coming the same values. Like it is not changing much.
So that means you should not go beyond that.
So for the next iteration, I should keep typing out the iteration.
Yeah. If somebody else would ask a question? Okay, so this is one of the very good methods, okay? And then one problem that we run into with this method is that if a loss function has got a very narrow valley, then it takes a lot of iterations to go there, okay? So gradient descent works well, but it can be very slow. It can take a lot of iterations. So to avoid that, there are other methods, but we will look at another method that makes use of not just the first derivative, but also the second derivative, okay? So in this method, we basically take the loss function and we do a Taylor series expansion, okay? And this may look a bit complicated to you, but this is essentially because I know I'm using vector notations, okay? Otherwise, it's a simple Taylor series. And then we take this function and set that equal to 0, and that gives an algorithm where the model update makes use of not just the gradient, but also the Hessian or the second derivative. And this is called Newton's method. So Newton's algorithm is then at each iteration, you compute the gradient and the Hessian, and this is your direction, and then you compute a step length, and that gives us the update, okay? So gradient descent is a special case of Newton's method where this H is an identity matrix, right? Okay? Now, this is a very powerful tool, but the problem is that, computing the Hessian is a lot of work, especially for a large number of variables. So typically what we do is we use some approximate values of the Hessian matrix, and we approximate it either using it to be a diagonal or some other methods. And there are some methods, those are called like quasi-Newton methods. Those are approximate Newton methods, but exact Newton is rarely employed because it's very, very expensive to compute the Hessian, okay? And also it's memory intensive. So what is the difference between the gradient descent and Newton's method? In gradient descent, we're going in the direction opposite to the gradient. In this Newton's method, what we do is using the gradient and the Hessian information, we approximate a parabola or a paraboloid in multidimensional space, and the minimum of that parabola is your next iteration, okay? So what you see is that if your objective function was close to being a quadratic function, this will converge much faster, okay? If you can afford to compute the Hessian matrix, okay? Okay, so we then look at some new developments. So let's say that I want to use a gradient descent algorithm, right? So for gradient descent, I have, yes?
If our data is having some noise, whether the gradient calculation can amplify that particular noise, so it may cause some problems during the optimization.
Yes, you are absolutely right. And that is why we sometimes apply some kind of smoothness on the loss function to get around that. Yeah. Okay. So let's say that we are doing some kind of some inversions. So let's consider some example. We have a lot of data points, okay, and we want to compute the gradient using all the data, because the gradient involves computing the forward solution, right? And then we take the gradient of the loss function, which is the difference between the observation and the forward synthetic data. So there are methods proposed here that can actually be very efficient for large data volumes. And these are called batch gradient descent, stochastic gradient descent, and mini batch gradient descent. So how do they work? It's quite simple. So the standard method that I talked about for gradient descent would be called batch gradient descent because it uses the entire data set. Okay? Now stochastic gradient descent, basically it performs a parameter update for each training example and level picked at random. So rather than using the entire data set, it will pick some data at random and then calculate the gradient. So there is a theory behind that shows when and how it can converge, but if you don't choose properly, you may sometimes run into divergence. So, but the idea is the same as gradient descent, except that how you compute the gradient is different. Okay, you're just picking some data sets at random and doing this. So here is an example of how it works. In a gradient descent, your loss function might look like this, but a stochastic gradient descent can have increase and decrease in error. Okay? So there is another method, it's called mini batch stochastic gradient descent. And that's actually quite beautiful. It's very beautiful. What it does, it says that rather than picking one data point at random, I can pick some batches of the data. Okay, so that is more powerful. So for example, you have, when you do machine learning exercises, you have, say, 100,000 data points or data vectors. So you can say that I will basically take batches of, say, 1,000. Okay? And it turns out that with that kind of sample, if it's chosen properly, you can get a very good estimate of the gradient. So mini batch would simply mean using small batches of the data at a time to compute the gradient. And obviously, you need less memory and it's less compute expensive, right? So this is one method. And then this is an example of how the convergence takes place. It's a two-parameter scenario. And this is your standard gradient descent. It smoothly finds this minimum. Stochastic goes up and down, and it may actually sometimes miss the minimum. If you look at the mini batch, it can, even though it goes up and down, but it actually comes close in. So mini batch is something that I would strongly recommend to use, okay? But there is another one. It's called, so these are batch gradient descent and mini batch gradient descent. You can look at those notes. So, okay. Yes?
We are taking different batches.
Yes.
So one batch could have a different global minimum and the other batch could have a different global minimum.
So that's a very good question. So it is, we assume that we can actually capture the gradient of the loss function for the data as good as using the entire data set. So the loss function is the same, okay? So that is the assumption. But you may run into some other problems if the batches are not chosen properly, okay? Okay, now this is a beautiful method. It's called momentum method. So in momentum, so what you saw in this picture where I was going doing gradient descent. So at each point, it only needs the local gradient, right? It does not remember what the gradient was in the previous iterations. And that probably is not a very wise thing to do, because once you have gradient information history, you have better idea about the shape of the loss function, right? So Polyak is this scientist who came up with momentum method, where he said that I will compute a momentum vector, which is nothing but the weighted sum of the gradient. As you go from iteration 1 to iteration 2, iteration 3, each time you update your gradient. And this has basically revolutionized the way we've been using gradient descent. This works really, really well, okay? And that problem that we had with this long valley, that can also be to some extent. So my experience has been that, not guaranteed, that if you use mini batches with the momentum information, it's called an Adam method. If you use mini batches with Adam, then it's called adaptive moment optimization. So mini batch plus Adam. This actually also helps you to some extent to get out of the local minimum because of the randomness, okay? And I'm not sure if this is theoretically guaranteed, but for many applications I found it has worked actually really well, okay? And this is very common in machine learning community, okay? Okay, yes.
Taking at different samples in a random way. For that, do we need to fix the step size, or it will take in a random way?
Okay. No, so step size is something that that is generally a constant. But in Adam methods, I haven't gone into details of that. They also use different step sizes for different parameters, okay? But otherwise, it's more or less the same. And then step size is a hyperparameter, so you need to play with it. Okay. 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 So that's all I had on optimization.